Hello, students, and welcome back. Today we are going to be looking at a couple of theorems that we will use to analyze graphs. The first one is called Rolle's theorem, and I will want you to be familiar with all parts of this. So what I've written in red would be the conditions or the hypothesis of the theorem, and what I wrote in blue is the conclusion. So you'll need to know that the conditions are that you have a continuous function on the closed interval, and that it needs to be differentiable on the open interval. And that just means that in the middle of the function, there cannot be any sharp turns. So continuous and differentiable. And then one other condition for Rolle's theorem to be true is that the y values, so f of a and f of b, have to be equal to each other. So I drew you a picture of that condition, and I'm going to continue to draw here in just a minute. So the y value for at point A and the y value at point B has to be the same. If that is the case, then we can conclude that there is at least one number c, now this is an x value, in the interval from A to B, such that the derivative at that x value at c is equal to 0. And so I'm going to draw a graph that meets those conditions. And I went ahead and put points at just a random y value so that f of a does equal f of b. And I can actually draw any function that I want to. So I could just draw a line. I could draw part of a parabola. I think I'm just going to make some curves here. And I just have to make sure that I have a continuous function and that I have no sharp turns. So Rolle's theorem says that there's at least one place where the derivative is equal to 0. Well, in mine, there's actually 3 places. Now, if your derivative is equal to 0, that means that your slope is equal to 0, which means that you would have a horizontal tangent. So I am going to look to see on the graph that I drew where I would have a horizontal tangent. So I would have one approximately here. And so I've got one C value, I'll call that C1. I would have a horizontal tangent right here. So I've got another one, and notice that it's in between A and B. And I've got a third one up here. And so I'll label that as C3. So it said that I would have at least one place where my derivative was equal to 0. And in that particular graph, I actually had 3 places. So Rolle's theorem. One way that you might remember how Rolle's theorem works is Rolle's has an O in it, and the derivative is equal to 0. So maybe that'll help you remember Rolle's and 0. Then we have the mean value theorem. That's your second theorem that we'll be studying today. The mean value theorem has two conditions that are exactly the same as Rolle's, and that is that you have to have a continuous function on a closed interval and a differentiable function on the open interval. Remember, differentiable means no sharp turns. Continuous means not lifting your pencil as you're drawing. So those are the only 2 conditions. Mean value theorem does not require that f of a equals f of b. So it just has those 2 conditions. If those are met, then the mean value says there is a number c in between a and b, such that the derivative, f prime of c, is equal to f of b minus f of a over b minus a. And if that doesn't sound familiar to you, I'll remind you that that is nothing more than the formula for the slope of the line. So y2 minus y1 over x2 minus x1. And so I'll talk to you about the two notes, but I'm going to actually draw the picture first. So I have A and B on a graph, and I have the f of A and f of B, and I intentionally did not make them have the same y value, although they could. So my only condition is that um, I have a continuous function. So I can draw anything that connects the A and the B and is a function without any sharp turn. So what's happening here is that the slope of the line that would connect points A and B is determined by f of b minus f of a over b minus a, the slope of that line. Go ahead and write that. And if I were to do the derivative, then that would give me the slope of the tangent line to that graph. And so somewhere between A and B, I should be able to draw a tangent line that is parallel to my blue secant line there. Now, I'm trying to freehand this. And I'll give myself another shot. Oh, I just got rid of my graph, but I'm not going to start over. I think I can redraw something here. So one more time, I'm going to try to draw a tangent line to that red curve that is parallel to my secant line. And that's pretty parallel for the purposes of this little demonstration. And so I have a C value, an X, located in between A and B, where the derivative, f prime of C, which would be the slope of the tangent line, so f prime of C would equal my slope, and the slope is the same as the one given by f of b minus f of a over b minus a. So the mean value theorem guarantees the existence of a tangent line that's parallel to the secant line through the two endpoints. And it also guarantees that there's some place in the interval where the instantaneous rate of change is the same as the average rate of change. So there's the beginning of your vocabulary for these two important theorems.